Hello there. So today I'll be making a video about order statistic trees. So if you haven't heard of what an order statistic tree is, essentially what an order statistic tree does for you is it allows you to find within a balanced binary search tree the kth smallest or kth largest item in logarithmic time. So what we need for this is first of all you need a balanced binary search tree, BST. So typically when you have a BST, so I'm going to draw one right here, which we'll use for a bunch of examples. So we have like a BST over here. So you can use order statistic trees in non-balanced BSTs, but having a balanced ensures the property of logn. So we have a bunch of numbers here. So if you want to find the kth smallest number, well, you have two approaches. Number one, you could do an in-order traversal. But this is Owen. So what you would do is you would go down here, and you would keep on iterating through these pairs until you get there. But if you're doing like the kth, where k is n, then you get O of n time because you're going linearly through the whole tree until you get to the last node. So it doesn't scale very well. So we want to try to use this idea for the augmentation strategy. So by augmenting number of children, we can get O of log n. Okay? So the way that this works, the basic idea behind this augmentation strategy, which only adds a constant factor to each node, so it doesn't actually change the memory constraint, is we know by the binary search tree property that all items to the left of a node are smaller than it. So we can have like a boundary line here at the time that these are smaller. So if I'm looking for the kth smallest, and let's just assume for the sake of this video that k belongs from 0 to the size of the tree. So it's 0 indexed. Okay? We know that if the number of children to the left of this guy is less than this number k, then I automatically know that the number is larger, because if it's there's 3 nodes here, and it's a pretty complicated topic to understand, but if you have 3 nodes here, and I'm looking for the 5th largest, and I know I can already ignore half of the tree, because I know it'll be on this side, because it's ordered. So I know that since it's larger already than 3, it cannot possibly be on this side or this one, it has to be on that side. So I'm going to go through a bunch of examples trying to explain it. So first, let's define the size. So for all nodes n in the tree, n dot size equals, so we want the size we'll just define as the addition of the left and right side plus 1. Okay, so for all nodes n in tree, n dot size equals left side plus right side plus 1. And if n dot size, if n dot left does not exist in tree, n dot left dot size equals 0. Okay, so by convention we're going to say that the size is if and only if the node does not belong to the tree. We'll say that the size is 0. So essentially what we have is we have all these, also have some nodes here that have size 0, which works in the edge cases. So pretty much what we have here is we can augment now the height. So 1 plus 1 is 3. We have 7 by our formula, right? And we have here zeros. Okay, So we have all these heights over here, and now we can get started with the algorithm. So we can define a class over here, bit of room. So it'll just be a straightforward class. We just need a node, some way to represent the root. So we can just have a node left, node right, int size, and all of the setters and getters inside here. Okay. So we pretty much what we want to implement now is this find kth item, right? So we can start implementing this method. So we're gonna do a public node get k smallest. So we have our root parameter, and we also have k. Okay, so basically what we're going to do is we're going to start off at this node, and we're going to go and we're going to look at the leftmost node just by convention. And let's first see what that node value is. So we're going to left equals root dot left dot size. So we can call it something else besides left, like left side or whatever you want. But anyways, so we take a look at the left. Now, if the left is equal to k, we have arrived at our destination. So let's assume, for the sake of completeness, that this tree only had one item. We're looking for the 0th smallest item. We look at the leftmost node, which will be an empty node. So let's assume we started off at this 2, as this is the root node. We're looking for the 0th largest item. It'll look left. It'll be 0. It'll be the same as k. It'll stop running. Okay. Now inside here we could also add, since if we don't pre-populate these, we could have a if statement inside here. If root dot left equals null, then left equals 0. But for the sake of this, I'll just leave it the way it is. So now we encounter the case where left equals k. Now we also have if left is less than k. So this is the case where we're starting off at the root of 10, and let's say we're looking for k equals 2, so the 3rd smallest item. We would go 1 to the left and continue iterating through. So in this case, we would actually recursively call get k smaller, and we would just continue on the left node. Since left is less than k, we would oh, actually I'm doing this backwards. It's actually if left is greater than k. Sorry, this is when we still need to go to the left. So 3 is greater than 2, so we're continuing left. So we do root dot left, and then we also keep k the way it is. Oops. Please. Awkward. Looks like I need to change a pen. Pen just died. But yeah, so I hope you guys see what I'm doing over here. Let's see if this pen works. Okay. Else, now this one's a bit tricky. So let's say we're going here and we're going for like the 6th largest item. So if we say like k equals 6, we automatically know that all of these items don't count, in addition to this item. So then we basically just do get smaller k, get k smaller, root dot right. Recursively already get rid of half, but now we do k minus left plus 1, because now we take these and we say, okay, it can no longer be part of this tree. We also eliminated this. We're here. Now we're solving the exact same problem, but we just have less children to worry about. We already excluded those. We already accounted for those nodes over there. So yeah, this is basically the syntax. that we need to do, and this is basically it. There isn't much to it besides this. So I can run through a couple examples right now, and we're gonna see how it goes. So now I got my own point. It's kind of sad. I just got this pen and it just ran out. So let's say we're going for the k equals 2. So k equals 2. So let's start at 10. So we're at 10. Oh look, it's writing something now. No. So we start at k equals 2. And we say, okay, let's look at the leftmost one. Get 3. Well, the left is greater than 2, so we're going to go over here. Now, by the way, what is 2? K equals 2, 0 and x is 3, so we should get there. So now we're at 2. 2 is greater than 1. So what happens here is I actually do 2. I go here, but I do 2 minus left, which is 1 plus 1, 2, gets me 0. Now I'm at 8, and then this one, 8, the leftmost child, none, so be 0. And 0 equals k, so I return 8. So we just went through an example, and clearly it worked. So in this instance, we went like this, and then we got the fact that it's 0, and we stopped. So the idea that we're trying to get from this is we basically just keep on going down, down, down. Even if we stop at a node that's over here, it'll still work. So let's say we're going for the second largest, right? So that'll be indexed 1 over here. So 1 would be the 6, because 0 would be 2, 1. So again, 3 is larger, so it goes left. 1, this is actually 1, so this actually works. You see here, we get k equals 1, because we're just going down, we're not changing k. K remains constant, so we're going down. And we get this node. So this is basically the order statistic tree, so it's an augmentation strategy. And you reduce the time complexity for finding a child. So you just simply augment it when you're building the tree, the number of children that you have. It's a pretty neat algorithm. So I hope you guys enjoyed this video. And thanks for watching.